Hi, my name is Corey Elias. I'm the project manager of LaSpace Mission Concept Academy's Team 42, and we are pleased to announce the development of the GO probe, which launches in September 2022 and arrives on Mars on March 2023. The GO probe is the next evolution in Martian research. Weighing in at exactly 5 kilograms, this is a mobile probe solution for the characterization of subsurface ice deposits up to 5 meters below the surface. Its primary objective is to employ high-resolution ground-penetrating radar technology to accurately estimate the properties of water feedstocks. The GO probe will land inside the walls of Tooting Crater, located in the Amazonas Planitia region. Our probe solution will arrive in 2023, over a decade before the estimated launch of NASA's human mission to Mars. The GO probe will employ vetted technology from NASA JPL, including the Crux GPR module, an innovative high-resolution unit. In addition, the GO probe will sport a space-ready GoPro camera, substantially increasing mission promotion and education. At only $16 million, the GO probe is a unique and creative solution for the determination and characterization of subsurface ice profiles across the Martian landscape.
The GoProbe EDL system will use a soft landing approach. Legacy systems or techniques were emphasized, giving the team access to real-world data from prior successful deployments. Much of the platform is based around Pathfinder's EDL configuration. The aeroshell will be a Viking-style 70-degree spheric cone containing a tetrahedral inner frame. The heat shield will be a 2 cm SLA 561V ablator. The system will slow via air brake, then parachute, then thrusters, to 0 meters per second at an altitude of 20 meters. Soft landing will be achieved using a Pathfinder-style airbag system.
The science payload consists primarily of the Construction and Resource Utilization Explorer, or CRUX, ground-penetrating radar module. Upon landing on Mars, the ground-penetrating radar will use 2 antennae, one to transmit and one to receive, to send radio frequency pulses into the ground at a center frequency of 800 MHz. These pulses will be compiled and analyzed in order to complete the designated scientific objectives. Information regarding the dielectric permittivity of the targeted stratigraphy to a resolution of 10 centimeters provided by the ground-penetrating radar will allow for the characterization of suspected subterranean ice deposits in Tooting Crater. Additionally, information from the ground-penetrating radar will help determine possible impurities in the ice deposits, assess the deposit's potability, estimate the ice-to-regolith ratio, and calculate the temperature profile of the targeted area.
The chosen landing site for the GoProbe mission is the Amazonas Planitia region, with Tooting Crater as a specified region of interest. Amazonas Planitia is an optimal choice for GPR-based data collection due to its high volume of subsurface ice and flat, expansive landscape. With the help of JMARS, this site was proved to be one of the best sites to gather information on subsurface ice.
Initial lander designs included the Hedgehog design put forth by NASA's Jet Propulsion Laboratory, as well as the JPL Puffer rover prototype. However, the final design was inspired by the Cube rover, a prototype developed by the private company Astrobotic. The original concept for the GoProbe's science payload was to focus solely on ground-penetrating radar data collection, the most accurate data source for subterranean measurements past 1 meter. However, after further research freed up extra mass, the science team decided to add LiDAR and a high-definition camera to the payload. A neutron spectrometer was also considered, but found to be too massive. The GPR was originally intended to employ a VHF antenna. However, it was decided to switch to a GPR that uses UHF and utilizes a Vivaldi antenna design. This compresses the length of the antenna to better match the size of the GoProbe.
Hello, my name is Sam Limatainen, and I'm here to introduce our engineering design. And here we have our GoProbe frame, which is made out of 4 CubeSat frames. Housed within that is our equipment deck, which holds our L-Space communicator device, our onboard computer, our 2 motor controllers, our onboard battery system, and our GPR transmitter and receiver. Forward of the equipment deck are our 2 motors and motor mounts. On either side of those, we have our wheels, which are modeled after the Mars 2020 rover wheels. And on either side of the frame, we have our Vivaldi antennas for our GPR. An equipment mast is provided to house our GoPro camera and our LiDAR unit used for navigation. The probe is covered in a protective cover, which houses our solar panels. A unit to correct our attitude while in motion is provided with a low coefficient of drag, which keeps us on a horizontal plane.
Moving on to risk analysis. The top of the page here is a graph of the likelihood versus consequence plotted out with each risk in its indicated position. The table below it is for each of the 9 risks that the current team currently has assigned to our project. And each of these risks have been reviewed and assessed with the NASA Goddard Technical Standard from 2016 in mind. And we have given reasons and the approach for each of these as follows. For safety, there are limited risks in terms of drop testing, safe distances, proper eyewear, PPE all need to be provided. But the main risks are actually going to be included of testing of the electrical systems and the battery itself at temperatures. The personnel working on the test should be aware of the cold stresses and how to properly triage those should care need to be provided. And then for fires, there's a potential with any electrical system that one may happen. So Class A, D, and E fire extinguishers should all be on hand when testing the equipment.
Hello everyone, my name is Oscar Gomez and I am part of the Mechanical Engineering Research Team. Today I will talk to you guys about the project timeline for our GoPro. Phase A is project initiation. As everyone knows, it's research and preliminary design. We go on to Phase B, which is design. Before completion of Phase B, we must submit a PDR by April 2019. After completion of the PDR, we must move forward to Phase C, which is manufacturing. Phase C involves the CDR, which has to be submitted by May 2021, and move forward into Phase D, which is verification, testing, and we're getting ready for launch. After Phase D comes Phase E, which is operations upon arrival, which is mostly data collection. Data collection upon when our GoPro decides to give out. After Phase E, we move on to Phase F, which is major reviews, where we close contracts and decommission.
The mission education and public outreach of the GoPro mission will focus heavily on effective and well-tested techniques already employed by NASA. Along with a summary and frequently asked questions page on the NASA website, the GoPro mission will have a presence on each major social media site. Every site will include a detailed description of the mission, its goals, and how this mission is relevant to NASA and society at large. Additionally, lectures would be organized at the high school and university level to educate youth about the mission and help inspire a new generation of NASA scientists and engineers. Lastly, a video series called Mars Busters would be created in which the team chronicles the progress of the mission. Each strategy is designed to encourage people to follow along with and be invested in the mission at large.
Our project is split across 6 fiscal years, from January 2019 to June 2024. Each year provides for a new phase of mission development and thus requires changes in personnel, salaries, equipment costs, material costs, and subcontracts. The total cost of our probe, including salaries, and all of the aforementioned items is approximately $16 million. The NASA Mission Directive has allotted this project $20 million to produce a finalized project, leaving us with $4 million to allot to future needs. The components of the probe itself cost approximately $5.5 million, making it one of the cheapest Mars-bound probes NASA has ever developed. 15 scientists and engineers will fly out to Cape Canaveral, Florida, in the launch year of 2022 for a team meeting and a viewing of the launch. This travel fee is estimated to cost $30,000.